In this lesson, we will discuss how to determine the hydrostatic force on a curved surface. Here we have a rectangular tank of liquid with specific weight gamma. The side walls of the tank consist of flat plane surfaces. Let's examine the pressure force along the right wall. Although the pressure force increases with depth along the wall, notice that it always points in the same direction, toward the right. This is because the pressure force acts normal to the wall and the wall does not change its orientation relative to the free surface. The resultant force on any planar surface, Fr, is found by first determining the small net force at each small piece of area dA along the wall, then adding all these small forces through integration. The small net force at a given area dA is equal to the specific weight gamma times the distance y from the free surface to the area times the sine of the wall orientation angle theta times dA. We are able to pull gamma sine theta out of the integral because they are constant, and the integral of y dA is the y-coordinate of the centroid yc times the wall area. For curved surfaces, integration is usually much more difficult because the pressure force does not have a constant orientation angle. On the right, we have a fishbowl filled with the same liquid. Notice that theta changes along the entire surface. This means that we cannot pull sine theta out of the integral and cannot develop a general equation to calculate the resultant force. However, it is still possible to find the resultant force on a curved surface using the following procedure. First, we need to specify the surface we want to examine. The drawing on the right shows a cross-section of a tank that contains a liquid of specific weight gamma. The right side of the tank is flat and vertical to a depth d, then becomes curved. The curved surface is highlighted in purple and has a height hs and length ls. The surface also has a width ws out of the screen. Next, we isolate the body of fluid that is adjacent to the curved surface, and we do this by creating planar surfaces. Here's what the fluid body looks like when rotated slightly. The volume of the isolated fluid body will be denoted as Vf. Next, we draw a free body diagram of the isolated fluid body. The weight of the isolated fluid body acts at its center of mass and points downward. We will call this force W. There is a pressure force caused by the weight of the fluid above, which acts at the top planar surface, and we will call this force F1. There also is a pressure force acting on the left planar surface, which we will call F2. For the last force, Newton's third law tells us if the fluid exerts a force Fr on the wall, then the wall exerts an equal and opposite force on the fluid. This normal force will be denoted as Fn. So if we can find Fn, we will know the resultant force Fr. We apply Newton's second law on the isolated fluid body to determine the components of Fn. The sum of the forces acting on the isolated fluid body is equal to its mass times its acceleration. Since the fluid body is not moving, its acceleration is 0 and the right side of the equation becomes 0. The normal force vector Fn can be broken into a horizontal component, which we will label Fh, and a vertical component, which we label Fv. The sum of the forces in the x direction is equal to 0, so F2 minus Fh is equal to 0. Rearranging the equation, we find that the component in the horizontal direction Fh is equal to F2. F2 is the resultant force on the left planar surface and can be calculated from the equation gamma times hc times the area on the left side of the isolated fluid body. hc is the vertical distance from the free surface to the centroid of the left planar surface and is d plus 1/2 hs. The area of the left planar surface is ws times hs. the sum of the forces in the y direction is also equal to 0. So Fv minus F1 minus W is equal to 0. Rearranging the equation, we find that Fv is equal to F1 plus W. F1 is the pressure force due to the weight of the fluid directly above the isolated fluid body. This weight is equal to the mass of the fluid directly above the top surface times the gravitational acceleration g. The mass of the fluid above is equal to its density ρ times the volume it occupies. We can combine ρ and g into gamma, and the volume of the fluid above is the height d times the area ws ls. We also could have calculated F1 from the pressure at the top of the isolated body P1, which is gamma times the depth d, times the area of the planar surface ws ls. The weight of the isolated fluid body is its mass mf times g. Mass is replaced by the density ρ times the volume of the fluid body vf. Rho and g can be replaced by gamma, and we find that the weight of the isolated fluid body is gamma times Vf. At this point, we would need to know the volume of the isolated fluid body to continue. And for simple shapes, it may be easy to determine this volume. However, if the surface is irregular, then it may be difficult to determine the volume. The magnitude of the normal force is the square root of the sum of the squares of the components, and the orientation angle is equal to the inverse tangent of Fv divided by Fh. The resultant force Fr is equal in magnitude and opposite in direction to Fn. If the curved surface is a gate hinged about some point O, we may need to determine the moments of all forces about the hinge. This requires knowledge of the moment arms of all the forces involved in the problem. If the fluid is static and the gate is not moving, then there must be no net moment on the gate or the fluid body. That is, F1, F2, the weight, and the components of Fn must produce no net moment. F2 and Fh both act only in the x direction, while F1, W, and Fv act only in the y direction. This means that F2 and Fh must have the same line of action, and Fh is at the same depth as F2. F2 acts at the center of pressure of the left planar surface. The distance from the free surface to F2 is yr. Yr can be calculated from the equation yc plus ixxc divided by yca. Yc is the y-coordinate of the centroid of the left planar surface and is equal to d plus 1/2 hs. A is the area of the left planar surface and is equal to ws hs. Ixxc is the second moment of the area about the centroid of the left planar surface. For rectangles, this is equal to 1/12 times the height to the third power times the width. If we take the moment about point O, the moment arms of F2 and Fh are equal to the distance between point O and point B, where point B is the location F2 acts at. We will call this distance YH. The length YH is equal to the distance from the free surface to point O, which is d plus hs, minus the distance from the free surface to point B, which is yr. F1 acts at the center of the top surface of the fluid body, so the moment arm of F1 is ls divided by 2. The moment arm of the weight is equal to the distance between the centroid of the fluid body and the left planar surface. You can look up this distance in tables for simple shapes. Notice that the moment arm of Fv, which we will call xv, is the same whether we take the moment about point O or point B. Additionally, since the gate is not moving, the sum of the moments about any point must be 0. To determine xv, we will calculate the sum of the moments about point B and set it equal to 0. By taking the moment about point B, the moment arms of F2 and Fh are 0. If we take the counterclockwise direction to be positive, the sum of the moments is Fv times its moment arm xv minus F1 times Ls divided by 2 minus W times xc. And we can rearrange the equation to solve for xv.